Okay, let's start again. We still have Dr. Triani speaking about, sorry, it's more about the interstellar medium now, right? Okay, as the previous session, we have more or less 1 hour of 30 minutes for the lectures. Okay.
Thank you, Bosti. Okay. All right. I hope you have a good rest, 15 minutes. Now I will focus on the study of dust and metals in the galaxy evolution and density modeling. So yeah, okay, let's just jump right in. Although I'm not sure if this talk can have like 1.5 hours, so if it ends earlier, then is it okay to start the hands-on right after this? Yeah, but we'll see. Okay, let's start with the background informations. So when we observe the galaxies, we not only see the optical regime, but like we have talked before, there are observations from gamma rays to radio now in galaxies. And now we know that the components of galaxies that dominating the UV to mid-infrared regime are stars, while from mid-infrared to a longer wavelength, it's the cold dust. AGN can be observed in X-rays and radio, and as well as the cold gas and hot gas. So all of the information, this multi-wavelength information, is usually presented in form of the SED, which stands for spectral energy distribution. So what you see here is basically, we have seen these images before, right? Like the image of one galaxies in radio, infrared, optical, ultraviolet, and X-ray. But now, instead of presenting it as an image, we integrate, so we sum up the lights of these galaxies in this wavelength as one number. So for example, in optical, so optical ranges from, for example, like 3,000 angstrom. So we just summed up all of the lights in galaxies, all of the lights in this image as one number in this and that wavelength. And we put that as a 1 point here. And then we pick another wavelength and we summed up again all of the lights in this image as a one number. And then we arrange that. So this is basically the intensity of light, and this is the wavelength. So this shows thousands of images. So this one graph can be expanded to thousands of images if we have the resolved information. But that is basically an SED. It shows the multi-wavelength information of galaxies in one graph. So instead of having 5 figures, we can just have this showing intensity and the wavelength. And then we can compute like how much the stellar emission, how much the nebula emission lines, and the dust emission in one graph. We translate this figure into lots of physical properties of galaxies. So we infer the star formation history, the metallicity, the total stellar mass, and the dust content of galaxies from the SED. And this is how we model the SED. Galaxies consist of lots of stellar populations. So stars usually form in bursts. So in one episode of star formation, the stars that is formed will have the same age and the same metallicity. So yeah, the star formation is episodic. So there's like one episode of star formation that transforms this much of a gas into stars. Then that stars belong to what we call simple stellar populations. So this is showing the spectra, the acidity of the stellar population with different age. So for example, if a galaxy is, if a stellar population is very young, so 1 million years old, it still have lots of lights in the shorter wavelength, so in the UV, because it still have young stars and have blue stars. So it appears blue. Lots of the spectra will pixel the blue. And as it gets older, because young and massive stars die first, then a very old stellar population, for example, 10 to the 10 year here, the red one, won't have lots of lights in the bluer part, but it will peak in the red part of the spectrum. So now, if we have the information, like if we have the model or the empirical spectra of a different stellar populations, then we can arrange that using the star formation and the chemical evolution of a galaxy. So this is showing star formation history. So the y-axis shows the star formation rate, and this is the time. So it shows like one episode of star formation. This is usually how we model the optical galaxies, while the red line here is more continuous, constant star formation, is how the classical model usually represent the spiral galaxies. And then a different stellar population will have different metallicity because it was born from gas with different pollution level of metals. So the stars that is born when the galaxies are still young and still not polluted with metals will have low metallicity because it's formed from pure hydrogen. But stellar population, so that the episode of star formation that happened later in galaxies, while the previous stars have exploded and have polluted the galaxies, will have different metallicity. So if we knew, so we can have model for star formation history and chemical evolution in galaxies to arrange the simple stellar population. So then we pick, so for example, okay, sorry, SSPs is the simple stellar populations, which is the stars, all of the stars get born in one episode of star formations from the same gas. So they have same age and metallicity. So if we have the history of star formation and chemical evolution in galaxies, then we can arrange different populations, stellar population in galaxies, and integrate all of the light. Then we have the composite, what is called composite stellar population. So now it's the sum of different simple stellar populations. So it is just integration. It's the sum of all of the galaxies, of all of the stars and galaxies that form in all of the episode of star formations. But what we observe is not this thing. What we observe is this starlight that has been attenuated by dust. So if dust exists in galaxies, then it will absorb the stellar light in what we call the attenuation effect. And the attenuation effect is different in different galaxies. So attenuation increase with, so this is the amount of attenuated light, and this is the wavelengths. So the attenuation increase as towards the blue. So the blue light is absorbed more than the red lights. And then because the dust is getting hot, it's getting heated by the stellar light that it absorbs, then it will emit the lights in a much longer wavelength. So this is the dust emission, and it will change the overall shape of the acidity. So rather than the blue line here, what we observe is closer to the red lines here. So using this model, that we can, like matching the model with the observed acidity, then we can infer all of these properties of a galaxy: the star formation rate, the chemical evolution, and the dust evolution. right? Yeah. So why we need to carefully model dust and metals is because, remember, the cooling process of gas are a very important process in galaxy evolution, and dust and metals are important gas coolant, and it can enhance the formation of the molecular hydrogen. So dust have surface, right? So dust is a solid particle. It's not like a gas. Because it is a solid particles, then it has surface, which can be the site for the formation of the molecular hydrogen, which is the main ingredients of stars. So the existence of dust in a galaxy can affect the star formation as well. And again, it changes the LCD by absorbing the stellar light and emitting in the infrared. So we correction for dust extinction or attenuation is really important. Otherwise, we have wrong galaxy's properties from the observation. But the usual model of like this usual semi-analytic model usually doesn't really care about dust. So they usually use a very simplistic treatment for dust, which has to end. Because like before, people focus on learning about stars, but because now I think like all of the model has got the correct, remember the star formation, like the luminosity function, then now people turns the focus towards dust. Let me see. So this is an example of lots of attenuation curve that is observed with different people, and it has different shape. So for starburst galaxies, so starburst galaxies are galaxies that have the episode of star formation very recent. It looks like the blue line here, while the Milky Way, for example, have the attenuation curve like the brown line here. This is the green and red line, for example, showing the attenuation curve from the small Magellanic Cloud from two different works, and it looks different. So that's why it's very important to do the attenuation correct, so then we can get the stellar emission correct in the LCD. In my research, so in this second part of the talk, I will focus on my research on implementing the dust process in a semi-analytic model called dust-DSH. I want to understand how baryon evolves in galaxies under the lambda CDM paradigm, and what is the importance of dust in the overall process of galaxy formation and evolution that we have talked before. So what are the key processes related to dust, and how do the dust properties correlate with all of the other important galaxy properties like the morphology and the gas content, stellar content, and then how does help us to predict the panchromatic, so the multi-wavelength galaxy emission. What I do is I implement dust model in a semi-analytic galaxy evolution called SAGE, and it forms a new model called dust-DSH, which I then use to study the origin of dust in galaxies and the evolution of galactic dust content. And then by extracting the star formation and metallicity history from the galaxy, we can model the stellar light. And then by having the dust history from galaxies, then we can model the dust attenuation and infrared emission. So then we can have like all of the ultraviolet to infrared LCDs. Now, the semi-analytic model is called dust-DSH. You can get it at this page. So github.com/dptriani/dust-DSH. Again, because it is a semi-analytic model, it runs on n-body simulation merger trees. So we have to have the merger trees first, and then we can run the model. But for testing purpose, the dust-DSH in the GitHub, I already provided the 3 files for the mini millennium simulation. So if the millennium simulation has box size of 500 gigaparsecs, so very large, which represent the universe, then the mini millennium simulation is the millennium simulation in a smaller format. So the box size is only 62.5 megaparsec, I think. Yeah, so it's a smaller size. So then you can test all of the physics in the model faster. And then after that, if you are happy with that, then you can move to the full Millennium simulation, which takes longer to run, with I think 512 files. So yeah, if you want to run that, then you can just like download the test stage and do the installation and try that to the 3 files for the mini Millennium simulation that has been provided in the model. So what are the processes that we have in this stage? We have the infall, so again, the gas infall to the halo, and then the cooling to the interstellar medium, and star formation. But now, the stars form from the pure pristine gas in this process, right? So pristine gas infall, it cooled down, forms molecular hydrogen, and so the stars now have been formed from pure hydrogen. As the stars evolve, the nuclear process in the core of the stars will burn the hydrogen and form more heavier elements. So the stars can have, like, depend on its mass, the stars can have lots of layers of different elements, and it can expel the elements in different parts of the evolution. So for example, smaller stars can end up only only after they reach the AGB, or the asymptotic giant branch. So then these stars can expel all of the heavier elements that is formed and pollute the ISM in the AGB phase. While, for example, massive stars can end up as supernovae 2, or binary stars can end up as supernovae 1A, and the supernovae explode and the stars pollute the ISM with the metals that is formed in its core. Now, because this is still gas phase metallicity, so these elements are in form of dust, in form of gas, but the ISM are so cold, and if it's cold and dense, then the solid dust particle can form in the cavity of the supernovae, for example. So in the correct environment, the dust can form from the metals that is expelled from stars. So this is how we made dust in the model. And now the solid particle of dust can accrete the gas phase metals in its mantles. So the size of dust will grow, especially in the molecular clouds. Like we talked before, it does have surface, and it can accrete material in the surface, and it grows. So not only in size, but also in mass. So this is the second formation channel for dust in the model. Excuse me. But dust can also be easily destroyed by the shocks generated by the supernovae. So it comes back to the gas phase metals if there is a very energetic supernovae. So it can destroy, the particles can be destroyed, and it can reduce the mass of dust, the overall dust in the interstellar medium. Now, the feedback process that we talked before, either supernovae or AGN feedback, brings out gas, cold gas from the interstellar medium to the halo, or even out to the ejected reservoir. But this gas, if the ISM is now polluted with metals and dust, now these feedback processes can bring the cold gas that has been polluted with metals and gas. So now the metals and gas can be brought up to halo, or even into the ejected reservoir from the cold gas that is in the outflow from the feedback. So now the dust and metals can also pollute the halo and the ejected reservoir. But because the halo and ejected reservoir are so hot, the dust can undergo more destruction, which is called the thermal sputtering. So it's the corrosion of the dust particle because of the very hot temperature. There's also another process called reincorporation, where, for example, where it's close to the infall, but instead of the pristine gas, because the baryon fraction must been kept, the ejected material can be reincorporated back to the halo. So now the dust in the ejected reservoir can be bring down to the halo and even in the interstellar medium by the process. So this is all of the process that is in the model. And I use that to learn about first dust origin in galaxies. Okay, maybe I'll have 2 or 3 minutes stop here to accept question. If you have question related to the dust processes before we go to the results. Okay, I'll have 10 seconds. You can raise your hand or type up in the chat box, or you can type in the chat box anytime and I will answer that in the submitted time. Okay, let's count 10 seconds.
Hello?
Yeah.
I was trying to, actually yesterday, 2 days ago, I was trying to get the GitHub module from for Dusty Sage, and I tried using pip install. It says an error that I could not find a version that satisfies the requirement for Dusty Sage. And I tried the git clone from GitHub, and then it also says repository, the Dusty Sage repository does not exist. So, yeah.
Okay. Do you use Mac or Linux?
I'm using Windows, actually.
Okay. So one of the prerequisite of Dusty Sage, unfortunately, I only built it to run on Linux or Mac. Sorry for Windows user. I haven't got to build it, to develop it to use Windows. But I think if you have access to the supercomputer, to the HPC, I think it can run there. So maybe to the server, and I will show you how in the hands-on session. So we will use the HPC to run that. But yeah, it is very unfortunate that it can't be run on Windows.
I understand. Most fences and astronomers, they use Linux and Mac. Unfortunately, I do not have Linux and Mac right with me right now. I understand. Thank you.
It's okay. Yeah, no worries. Yeah. So yeah, another question. Okay, right. So now I use Dusty Sage in.
Hello.
Yeah.
Sorry. So you are just modeling dust. So in dust, you are just incorporating dust, or the dust plus gas.
Dust plus gas. So all of the process that I explained before in the first lecture, like the gas cooling, star formation, there's already a model that do that called Sage, and then I implement the dust on top of everything there. So there's dust and gas process and star formation.
Okay. So for gas, so how you are incorporating gas? Because what I understand is from these process, from feedback and everything, the gas would not be in a single phase, right? So it would be in multi-phase. The gas present in the halos and everywhere. Like there is a constant interplay between CGM and IGM. Okay.
That's
so
true.
Because of that interplay, the gas is in multi-phase. So how you incorporate the multi-phase gas in the model, or you are just incorporating a single phase gas?
No, thank you for the question. Yeah. So the gas, the model basically have 3 buckets for gas. So there is a hot gas in the halo, cold gas in the ISM, and the hot gas out of the system, which is what we call the ejected reservoir. So this is what is the theoretician's version of the IGM, CGM, and the ISM. So the cold gas will, there's this 3 bucket for gas is represent the multi-phase of gas. So we have the hot gas that represent the CGM, and the cold gas that represent the ISM, and the ejected gas, which represent the intergalactic, the IGM. Yeah.
Okay, yeah, thank you.
Is there any other questions? All right. Right. Let me think. Okay, so now we will talk about the results of the model. So what I do is I want to learn what is the origin of dust in galaxies. And this is the short version of it. So what I've show here, the pink region here is the star formation rate density that I've shown before. Remember the cosmic noon? So this has different axis scale, so it looks a bit different, but this is basically the star formation rate density versus time since Big Bang and redshift, and it shows the cosmic noon around redshift 2. When we model the dust, and the results of the model is the dust have the same thing. So the black line is the total dust formation rate density, and it shows that it peaks around like redshift 2 as well, but it's not increasing as much as the stars, but it rather flats. And if we see at the 3 different processes for dust in the model, there's the stellar dust production, and there's the growth in the dense molecular clouds and the destruction by the supernovae. Then we see that around this peak, there is a switch in the primary dust mechanism. So if we only look at the stellar dust production, it mimics the star formation rate density very closely. So after peaking around redshift 2, it goes down. But because now the galaxies have enough metals in its ISM, in its molecular clouds, then the dust can grow by accreting these metals. And this metal accretion is like more efficient than the stellar feedback since the peak. So there is a switch in the primary dust mechanism. But how do we observe this, right? Because we cannot observe the individual dust production channel for now, right now. This switch then reflected in the relation between the dust formation, the dust to metal ratio and the dust to gas ratio versus the gas phase metallicity. So the dust to metal and the dust to gas ratio is basically the ratio between the luminosity, like the infrared luminosity and the total gas luminosity. And then here is the gas phase metallicity that we got from the emission lines. And we see here that the characteristic at redshift 0, for example. So at redshift 0, it shows the same thing. So this is show the dust formation rate density for all of the galaxies at redshift 0 with different metallicity. And we see like a critical switch here where the growth by accreting metals supersede the stellar formation for dust. And we see that in the dust to metal ratio, it caused this change from decreasing relation to increasing relations. But this is like in different, like in one redshift. So if we can observe this in different redshift, then we can confirm like what the model said about the switch in the primary dust mechanism. So that's basically like the TLDR for this first results is at present universe. Now, all of the galaxies mostly form dust by accreting the metals instead of the stellar dust production. And the dominant dust production mechanism affect the dust to metal ratio, which shows the dusticity, like the amount of dust in the galaxies relative to their metals and their dust. Then I also want to see how the galactic dust content evolve with the morphology. For example, like how is the different dust content in spiral and elliptical, and how that ties to the star formation and metallicity. So this is showing the total dust mass in the interstellar medium and the total stellar mass of the galaxies. And we see that there is this an island here, which shows galaxies that are rich for dust. But there are a large distribution under this red line that has less dust than its dust-rich counterparts. So then I divide all of the galaxies in a model based on this red line and define the galaxies above this as dust-rich and below this as dust-poor. But interestingly, we also find the dust-poor galaxies, but that has abundance of dust in their halo. So we define that as halo dust-rich. So in this ISM dust-poor galaxies, we separate another class that has abundance of dust in their halo. And this ISM dust-rich galaxies we define based on their star formation. So there are quench dust-rich galaxies and there are star-forming galaxies. Now, this diagram shows so many things. So let's break it down slowly. The y-axis shows the bulge to total mass ratio. So the low ratio will be held by elliptical galaxies. No, by spiral galaxies. And the high ratio is like bulgy elliptical galaxies. So elliptical galaxies are here, spiral galaxies are down here. The x-axis is the star formation rate divided by stellar mass. So it shows the specific star formation rate. We use the specific star formation rate because we don't want the star formation rate to be biased. Massive galaxies are usually having a larger star formation rate, so solar mass per year. So if we divide that by the solar mass, then we have the rate of star forming per year only. So like the region here is the galaxies that have very active star formation, while the region below here, like in the left, is galaxies that is basically quenched. The colors will show the metallicity in galaxies, and the size will show the mass, right? So in the ISM dust-rich galaxies, all of the classes with different stellar mass, total stellar mass, occupies the spiral star-forming region with the average metallicity around 9. So it's pretty high. When we compare that to the quench ISM dust-rich galaxies, of course, the quench will have lower star formation rate, but everything is spiral. So now we know that the spiral are very rich of dust in their ISM, but the quench galaxies, interestingly, have higher metallicity. So then we know that in the process of quenching, like more stars will be formed in the ISM that has more pollution than the one that it's like still have continuous star formation. Now in the ISM dust poor group, we have the halo dust rich. So now it occupies a very different place in this region. So it occupies the high bulge to total ratios. It's very elliptical with low star formation rate and very low metallicity. So these galaxies, because it doesn't have any metals, then it cannot grow the dust via the metal accretion. But the dust poor, so this is the dust that is like poor in the ISM but has lots of dust in the halo, and this is like the true dust poor galaxies, which interestingly have higher metallicity than the halo dust rich galaxies. So there is these strange classes that have lots of dust in their halo but very little of metals. So then how does that dust form, right? Then I didn't show it here, but we find that the outflow rate of the halo dust rich is much higher than the dust poor galaxies. So these galaxies must be ISM dust rich in the past, but because they have a very energetic outflow and feedback, then they just like expel all of the dust to their halo. And that that's how they expel their metals too, and that's why their metallicity is very low. So this is kind of confirm like the typical spiral and ellipticals that we talked about before. Like the ISM dust-rich galaxies usually represent the late type population, while the ISM dust-poor galaxies more represents the early type populations. And then my third work is about the dust effects on the acidities. But like before we talk about this is quite different. So we will talk about more about the luminosity functions here. If people have any questions about the physical properties of dust and how it compares with the galactic dust content, I'll wait for a couple of seconds for people to raise their hand or have to type their question in the chat box, or just unmute yourself and ask. Okay. Right. Let's move to the acidity. So how does affects the spectral energy distribution of galaxies? I have this acidity model which can be accessed from the web app. In Streamlit, I'll share this presentation, so then you can start playing with that. The full version is in my GitHub, and it requires installation. But if you want to play, maybe start with the web app first. So what I do is I extract the star formation and metallicity history from dusty stage, which looks like this. So for example, let's see like the real stochastic star formation and metallicity history from the model. The spirals are very, like they have lots of episodes of star formation, and it's still going strong until now. It still have like 20 solar mass per year star forming until now. While the elliptical looks maybe like a spiral in the past, but it has died down a long time ago. So if we have this star formation history, then I use a set of the catalog that shows the spectra of different stellar population spectra from Brujol in 2003. Then I can make the acidity of galaxies from UV to infrared, but this is like pure stellar. So all of the stars acidities are here. And this is what the model looks like, while the points, like the purple points, are the observation at redshift 0 from gamma survey here in Australia. So then having the description of stellar, then we also have the description of dust. So using the dust surface density from the model, we can compute the optical depth for the attenuation. And then I use a set of 2 sets of infrared templates from Dale and from, so the Dale is more empirical and the orange line is more theoretical. And then we can have different sets of acidities full from UV to for infrared with different line representing different models. So I varies lots of things in the model. So I varied the attenuation parameters and also varied the infrared parameters. I have one model here that uses a single value for all of galaxies, which is the approach usually adopted by the observers. And we see that at redshift 0, this is the far ultraviolet to near infrared luminosity functions, right? So this is the AB magnitude, and this is the number density of galaxies. This is the bright one, and this is the fainter one. We see that the model is still over-reproduce the bright UV luminosity galaxies. It's either that, or we still haven't found enough bright UV galaxies in the observations. But so this is the unattenuated model. The cyan is the pure stellar spectra, but it's clear that we really need dust to bring down the luminosity function to the observed values. And we have two recipes here. So the blue line here is the CF00 is the single attenuation prescription, while the black and dotted red lines are the recipes that use varying dust mass for inferring the attenuation, and it works much better. Now here's the lots of luminosity function in different bands. So this is UV, this is optical, UGRIZ is the SDSS optical, while K band is near infrared. And we see here that it doesn't really matter in the optical to near infrared. There's the difference between the unattenuated and the attenuated lights are getting smaller and smaller and smaller until the K. So basically at K band, the dust is not really important. It's all stellar. While in the U band, it's still a bit important, but the importance grows like decrease with increasing wavelength. So U wavelength is lower than G here and lower than R. R is red, U is blue. So then in the mid-infrared, this is where dust emission starts to be important. We see that after K-band is near infrared. So this is 3.6 micron wavelength. It is still like dust doesn't really still make difference. But at higher wavelength, this is again different dust attenuation, and our model really struggle in matching the 8 micron luminosity function. But that's because there is a contamination of AGN at this wavelength. So if we change the AGN fraction of the model, then we can like match the data, like the observed luminosity function. But AGNs are really complicated. So it needs to be modeled very carefully. And because this SSH hasn't, so for example, the SSH has the AGN feedback, right? But we haven't modeled the AGN emission very carefully. So that's why we'll leave the mid-infrared now and to work for it later. And the far infrared is usually just only dust. So the mid-infrared is contaminated by the emission of AGN, while far infrared is usually just like cold dust. And using the model, we can agree well with the data using the, the black line is the default model here, using the varying attenuation recipe. So model with dust mass parameter, the orange line here, works better with our model. The model with the blue line here is the green line, but the data sits between those two models. Yeah, and in the high redshift universe at K-band, so remember K-band is where stellar spectra are the most important. So that's not really important here. We have an excess of faint galaxies here. So this is bright galaxies, this is faint galaxies. The model in faint galaxies has much higher density than the observation, which could be probably can be solved by implementing different reincorporating time scale in the model. Remember, like the reincorporation of cold gas in the halo. UV and infrared at high redshift is very important when we want to study the star formation rate obscured by dust. So red galaxies are used, like star forming galaxies usually appears red because they have lots of dust as well. So there's the degeneracy of the age of stellar population and dust in the infrared. And now I come to my conclusion that now we have covered all of the processes for galaxy formation, from the gas to stars and the dust. It is all have interplay between the component and the, like in the last 2 decades, the processes concerning stars has been the focus. But now, because I think we have a good, like see, like the K-band luminosity function all looks good, but the UV and infrared still has to have lots of improvement, then we have to really shift our focus to model dust, so then we can like match the constraint from the observables universe much better. And using semi-empirical models are a good way to explore all of different physics, all of the different processes and interplay between the stars and dust and gas. But we have to be careful, and it is important to use as many observations as the constraint for the model. Now, the study that we got from the CSH is that we can now match the observation of local galaxies, and we know that there's a critical metallicity and a critical point in the dust production mechanism where there's a switch. Remember, there's a switch between the stellar production and the dust growth that is different from the star formation rate density, and it drives the dust production channel in galaxies. And we also learned how the dust content correlates with morphology, with the star formation rate and metallicity, and generating the luminosity function by using the model dust mass results on quite a good match with the observation of local galaxies. So after this, let me see. Yeah, so after this, I'll have the hands-on, but now we have time for questions. Is there any questions? Okay. Right? Okay, if not, then I think we end 15 minutes early. Shall we start the hands-on session now, or shall we start the break now and comes back to the hands-on later? Also, if you want to contact me, like asking question, I'm always open. You can contact me in my email address here, so dian.triani@anu.edu.au. And I understand Indonesian, so if you want to email me in Bahasa Indonesia, it's okay as well. Oh, there's a question.
Questions?
There's a question from Aulia in the chat box. Can dusty stage be used for the other dark matter models? Yes, for sure. As long as we have like the halo merger trees, we have tried dusty stage using various dark matter simulation models. Not only the Millennium, but Millennium is what we use in the paper. So.
Any other question? If not, I have one, I think. Do you plan to incorporate any magnetic field into your model?
Oh, magnetic field is the different, is it even more complicated processes in galaxies. So for now, not yet, but in the future for sure. So I think for now, my focus is still on studying dust, but magnetic field will add another layer of complication, and it will definitely be interesting to study in the future.
Okay, thank you. Any other question from the audience in the seminar room?
Yeah, so are these dusty sage models and these simulation can be used to constrain the dark matter properties? Because we have several models, theoretical models for dark matter, sorry. So is it possible to constrain some model of dark matter from this dusty stage?
Yeah,
So,
thank you for the questions. So we can output the properties of dark matter halos. So for example, the virial mass and radial mass, velocity. There are several properties of the halo that can be output from this stage, and it can definitely, so it gets constrained from the dark matter observations. But what kind of like constraint that you have, for example, in like dark matter properties, is like, for example, halo mass function? Is that what you're talking about?
yes, let's say we have a WIMP dark matter model. So what dark matter models you are using in this dusty stage? I'm not sure on that.
Yeah. Oh, so you mean you have the dark matter models,
Yes. So can we
and
constrain
then you
like
want to constrain that? So you want to use different cosmology. Is that what you're saying?
yes, yes.
Okay. For now, no. So now it's only used the lambda CDM models. So it's limited by that. So if you have other models for dark matter, I don't think it will work. But you can try that and see how it compares with observations, I think. But I haven't really, I haven't really worked with other dark matter models. So I'm not sure.
Okay, so we can also like constrain the cross section of something. There are different parameters, different constraint properties, even in WIMP dark matter models. Are these possible to constrain with this dusty stage?
With that's the stage model. Yeah, that's interesting question. I have to go back to you with that. But yeah, I haven't really explored the dark matters part of the model, but I think it's possible. But yeah, I haven't really seen like the results for that. So I have to check and go back with you for that
Okay.
questions.
Yeah, thank you.
No worries. I'm on Slack as well, so I'll reach you out
Yeah,
there.
yeah, thank you.
Okay.
Do you want to take some more questions, or we are proceeding with the
Hands-on?
hands-on? Yeah.
I think we can proceed with the hands-on.
Okay.
Until what time is the second session?
11:15.
11:15. Okay, right. Okay.
So go ahead.
Thank you. Okay, so now let's do the hands-on part. So if you have the HPC, I think Dr. Ibnu has installed SSH in the HPC, or if you want to install it in your own computer, so you can go to the GitHub page and follow the installation procedure. Now, okay, let me show you what's in the GitHub. So once you go to the GitHub, so you can download all of this, but inside this source, aux data, and then millennium, there is this minimillennium.par file that looks like this. So this is the parameter files that you need to run the model. So what you need to make sure to be correct is the output directory exists. So here I use the source/aux data trace minimillennium directory. But if you want to put all of the results in another directory, then you make that directory and you put the path to the directory here. There are 7 files. So sorry, there are 8 files in the mini millennium simulation. So numbers 0, 1, 2, 3, 4, 5, 6, 7. And if you want to use all of those files, then use first file 0 and last file 7. If you only want to try, then use last file anything you want between 0 and 7. So you can use 2 files. So first file 0 and last file 1, and etc. The number of outputs here sets the desired number of redshift outputs. So the list of snapshot here is there are 64 snapshots in the mini millennium simulation. So the last snapshot is the redshift 0. So here in the default, I set 8, and it shows redshift 0, 1, 2, 3, 4, 5, 6, 7. But if you only want to have redshift 0 results, then just put num outputs 1 and put only 63 here. So you can command it using a percent, like a percent symbol. Then yeah, so you can change this, and then everything here, just leave it as it is, because the trees file is in the mini millennium, and a file with snapshot list is here. Then there is this recipe. So there is several stop formation prescriptions. So the original formula is number 0, 1, and 2. Usually we use number 1. There is also the options to turn on and off the AGN feedback and the supernova feedback. But like for now, for like the first run, maybe just leave it as it is. But remember, you have to change this. Like you don't have to change it, but you can change this as you want. And then in the back to the home, in the analysis part, there is a Jupyter notebook called IVC exercise. So if you open that, I hope it can open. Yeah, if you open that, then it shows, so you run the model first. Running the model is like this. So you git clone, you make it. If you cannot make it in your own computer, then access it using the HPC, and you run it by typing ./stage and then path to the .par. So this is you write src / blah 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 / minimillennium.par here, and it will run. And after that runs, check that directory that you put in the output there, and if there's model there, then open the analysis and the IVC exercise. So this is how you reading properties from the model. So the box size here is 62.5 megaparsec if you use all of the files. So if you use 0 to 7 files, if you use only 2, then put 2 here. So then it will compute the box size, the corresponding box size. And put the directory here is where your resulting directory is. And this is all of the properties from the model. Then we have the pressure, stellar mass, bulge mass, everything. And the reading process is here. So then, for example, the stellar mass at redshift 0 is this. So 0 is at redshift 0, 1 is at redshift 1, blah, blah, blah. So there is an exercise here. So for example, number 1 is, what is the percentage of galaxies that are more massive than 10 to the 7 of sun? And if you're familiar with Python, if not, then you can always ask question. I will be here until 2 p.m. So you can always ask question. You can chat me. Okay, getting some error. I think someone already installed the Dusty Sage. Can you see the Dusty Sage directory in the HPC? If yes, then you can work with that. So probably make your own directory for running it. So instead of run it in the mini millennium, make a directory for you with your name and change the output directory. Can install in your PC. Okay. What is it said? That it can't be installed? Is there any error message? Yeah, GitHub now have changed their like policy in cloning. So let me see. So you can download. So this is for Sophia. You can download the here. So if you go to the GitHub page, then do code, open the code, like the green code, and download zip. And you can extract that if you use your own computer. So for Megat, good. Sorry, no worries. So after cd /sh, you need to open the src and aux data and 3/mini millennium. And there's this mini millennium.par that you can change the output directory here. So it will show you the src aux data 3/mini millennium. Maybe copy that and then make your own directory somewhere. So for example, you can make dir output or make dir Megat, and you can change that path here to your own directory. And to run /sh, you can type this /h and path to your own directory. Yeah, so you need to copy or just like type the path to your directory here to the mini millennium directory. Oh, yeah, you have no, you don't have to copy the whole code. You just need to copy the path. So then it's correct. Like the whole path of the output dir. So the path from this. You don't have to copy that as well, actually. So just like this output directory. Just remember where you put the mini millennium.par is. And okay. Okay, let me see the PowerPoint again. So let me know if you have, right. So this is how you run the dusty sage ./sage, blah, 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 like the path to your mini millennium file. And if you have, I think you have to wait around like 5 minutes for it to finish running. If you have finished running, please raise your hand or type something in the chat box so I know that you're successfully running it. Then I can show you how to access the Jupyter notebook in the server. Okay, for my guide, a blank page. When I use Film, I see a blank page with. Okay, so if you CD to SRC, or don't do anything, just run the Dusty Sage by typing this. I think it should be fine. So just skip to this page, skip to this step and see what you got.
Hi, Pipit. We have to just change the output directory in this mini millennium.bar, right? Hello.
Yeah, sorry. Go ahead.
Yeah, Pipit. So we have to change the output file in this mini millennium.par, right?
That is, yeah, that's correct.
Okay, output directory.
I don't know how it works with the HPC, because if you run that and other people run that, then it will like, overlap, like, because
Yeah,
I think,
it's better to create a different folder.
yes. So make a new directory with your name and change the output directory and run that inside that directory. Okay. I think the SSH on HPC Brain is already made. So I think it's already installed. So what I think you need to do is make a directory with your name in the mini millennium, for example, or anywhere, and then change the output directory inside the .par file to your output directory, to the new. So for example, for Megat, you can try make dir blah 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 / Megat, and then change the output dir. So let me show you. When you vim, okay. So there's this mini millennium.par. You change this, the simulation gear, with the new path to your own directory. So for example, Megat, oh, sorry, it's not this one. So for example, Megat, you change this instead of src aux data, blah, 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 just add Megat in the end of that. So change the output there in the mini millennium into this. And after that, try to running that. Yeah, you don't need to run in the HPC. Oh, do I still? Okay, if you don't need to change it, then it's okay. I'm just afraid that if you run in the HPC, then all of the, yeah, so if it's running fine, then it's okay.
For me, it's showing some errors.
What does it say?
I miss a value for tag in different files.
Oh, okay. I think you put the wrong path of the mini millennium. So when you're running it, instead of, so let me show. share the screen again.
So
So when you're running it, just use this one. So you don't need to change the path when you're running it. Just use the path to the mini millennium.
yeah, I have used this part on here. Ah, okay, yeah, okay, I got it. Nice. Yeah, I got it.
Good. Thank you, Ali. Yes, I think I renewed the model with the exercise. So if you want to get exercise, do the git pull. So after running it, and if you cannot find the new exercise, then do git pull.
This IVC exercise is in which folder? The analysis.
In the analysis, yes.
Okay. We need to get folder.
You need to git pull because I just renewed the version, yeah. Yeah, and if you want to open the Jupyter Notebook in the HPC, then you can do this. Okay, it's running. That's very good. Awesome. And I think the host name in the HPC is login only. So this is two dash, okay? So dash dash and dash dash. Hmm. Okay. Let me think. So for
For
me,
me,
guys,
it is terminated somehow. I don't know.
the what?
For me, it is terminated. It says
Ah,
done file one. Then after done file two, it's terminated.
okay. That's really strange. Is that in HPC or in
Yeah, HPC.
your own?
It's in HPC.
Hmm. So you can only run. So it's probably because I think it's because the HPC was oversubscribed. It's okay. I think it takes quite a time. So you can use a batch. Yeah. So thank you, Mbak Sulis. I think it's because the HPC is oversubscribed. So you can use a batch mode, I believe. Or if you just want to run a fewer files, it's okay too. But as long as you remember to change the box size, instead of using 8 files, just use, for example, 2 files. It's fine. Okay, for my God. Hmm. Yeah. Oh, sorry. I lost track of the chat. Okay, let me see. Oh, so your mini millennium doesn't have the mini millennium dot par. Thank you, Shubham.
Yeah. Okay. So how many files does it have to run? Till file 7, I guess, right? 0 to 7.
Till 5. Yeah, the maximum is 7.
Yeah, okay. So now it has run. Nice.
Very good.
It's done. Okay.
Okay. So open that .par files using Vim. And you can change the output directory into your directory. And when you run the test.sh, type the path into the .par file. Okay, I think we have 2 minutes left. How do I get out of a file again? So in Vim, yes. Thank you, Ali. Right. Oh, you see the, yes. Good work. Okay, I think we only have a few minutes left, and some of you have run test.sh successfully, and we can continue on. I don't know how 1 p.m.
1
Is it?
p.m.
Yeah. Okay. All right. Thank you, everyone.
Okay. Okay, everybody, we come to the end of this session. Let's thank Dr. Triani for the wonderful lectures today, but we still have another session for hands-on. Yeah, we'll continue at 1 p.m., okay? Let's give a big applause to Dr. Triani.
Thank you so much.
Okay, see you again at, we have a photo session.
Okay.
Okay, everybody, just get ready. Those on Zoom, please open your camera. We'll take the picture. Okay, Chandra will take the picture for us.
Okay, please, everybody, to open
Wave
your
your
camera.
hands.
We will begin the photo session shortly. Okay, I will begin right away from the first slide. On my mark, 3, 2, 1. Okay, the next slide. 3, 2, 1.